Good morning, my dear friends. I hope you all are doing great. So today we'll be talking about enthalpy change during phase transformation. So look at this particular term, phase transformation. So remember, we will be dealing with physical process. We will not be dealing with the chemical reaction here. If you look here, the standard enthalpy of fusion, enthalpy of vaporization, or standard enthalpy of sublimation. So these are all physical process. So we have to see what will be the change in delta H naught during all these physical process. But first of all, let us understand in phase transformation, my dear friends, what you can have. In the first case you will be converting a solid into liquid. And in second case you will be converting liquid into gas. And in third case you will be converting solid directly into the gas. So these are basically the phase transformations, my dear friends. These are your phase transformations. And during this process, you have to calculate delta H fusion. And during this process, you have to calculate delta H, my dear friends, vaporization. And that is standard. And here you have to calculate delta H sublimation. So my dear friends, we will understand them one by one. But before that, let us understand here what is a physical process. A process in which state of a system or in which a state of a substance, we can tell, changes. Okay? So a process in which only state of a substance changes. So have a look here. If I have water with me and that is ice, solid, I will convert it into water liquid. You will see that the state has changed here from solid to liquid. Yes, but substance will remain the same. This is H2O, this is also H2O. A process in which only state of a substance changes. Yes, but the substance itself remains the same. Yes, but substance itself remains the same. So my dear friends, if I take on H2O, let us suppose, I will take it in liquid state. I will convert it into H2O gas. Again, only the state is changing from liquid to gas, but substance remains the same. Who is the substance? Water. H2O and H2O, same, there is no change. If you convert, let us suppose we have carbon dioxide. It's in, let us suppose, solid state. We call it as dry ice. If you convert it into carbon dioxide in gaseous state. So, what is changing here? Only the state is changing. You are going from solid state to gaseous state, liquid to gaseous state, and solid to liquid state. A process in which only state of a substance changes, but substance itself remains the same. H2O, H2O, so substance is same. CO2, CO2, substance is same, but only the state is changing. Solid to gas, liquid to gas, and solid to liquid. So we call it, this process, as physical process, my dear friends. I hope you have understood this thing. And we will be calculating for these three processes as delta H naught fusion, delta H naught vaporization, and delta H naught sublimation will be calculating under standard conditions. Now you will be thinking that what is basically the standard state of a system? Let's write down that point also here. Standard state. In previous class I have told you about the standard state. A state of a substance, okay, at 1 bar pressure and at temperature of interest. And that temperature of interest is usually 2 298 Kelvin temperature. A substance, a state of a substance, okay, at 1 bar pressure and at temperature of interest, usually 298 Kelvin. Remember one thing, when I talk of temperature of interest, my dear friends, usually in most of the reactions you will take it as 298 Kelvin, but it's not necessary. With respect to reactions or with respect to physical process, yes or no, you can change the temperature. Yes, if 298 Kelvin is required, then use 298. If 300 Kelvin is required, then use 300 Kelvin. That means we have to use the temperature of interest. But in most of the reactions, we are using 298 Kelvin. Remember that. We have to use temperature of interest. Means the temperature required for that physical process or that chemical reaction. Yes or no? The temperature of interest. But in many of the reactions now we are using 298 Kelvin. That's why usually 298 Kelvin. I hope you are understanding, my dear friends. And remember also one more thing. In a standard state, remember, a substance will be in its pure form. Yes or no? Remember, this substance, okay, will be in a pure form. So a state of a substance, yes, at 1 bar pressure and temperature of interest is the standard state of that substance, my dear friends. Okay. Now, I hope you have understood these terms here. I will go further to discuss them one by one, my dear friends. Okay, please make note of this. Friends, now let us talk about the first point here, that is standard enthalpy of fusion. Okay, the enthalpy change, that is nothing but it is your here delta H, and we know that it's a standard enthalpy, so I will write on delta H naught. And we know that we are talking about fusion, so this will be your standard enthalpy of fusion. So this will change. It can be positive or it can be negative. So let us see what is the value. The enthalpy change during conversion of 1 mole of solid. That means you are taking a 1 mole of a solid substance. Look here. Here I have 1 mole of water. And that water is here in which form? It is in the form of ice. That solid is nothing but ice. Correct, my dear friends? Into its standard state. That means this water has to be in the standard state. So this water should be in its standard state. Okay? And what will be the standard state of this water, my dear friends? What are the conditions which I should take on? Here, the conditions which I am taking on for the standard state is that solid, water solid will change into water liquid. This is known as fusion. It's also known as melting. Remember that. You can call it as fusion or you can call it as melting, my dear friends. This is a term. Now, if I call this water solid as a standard state, then I have to fix two things. Two things will be, it should be at 1 bar pressure. Yes, so this physical process should take place at 1 bar pressure. And second thing, I need the temperature of interest. Usually 298 Kelvin I told you, but it's not necessary. In many of the physical and chemical reactions, it is 298 Kelvin. But here I have to see that at which temperature this process is taking place. Is it taking place at 298 Kelvin, that is 25 degrees Celsius? Or the melting of ice will take place at 0 degrees Celsius. We know that melting of ice will take place at 0 degrees Celsius. Ice will start melting at 0 degree. Yes? So now, my dear friends, here I will take on the temperature as, just a minute, 273.15 Kelvin. It's equal to 0 degrees Celsius. So at 1 bar pressure and 0 degrees Celsius temperature, you can also call it as the temperature of interest. So this process will take place at, 0 degrees Celsius temperature. And this 0 degrees Celsius we are keeping a constant temperature. So this temperature of interest here is constant. So what is the constant temperature here? 0 degrees Celsius. What is the temperature of interest? 0 degrees Celsius. And what is the pressure required here? 1 bar. So this water solid will be converted into water liquid. And conversion of water solid into liquid is known as melting, or you can also call it as fusion. So now, in this process, my dear friends, I told you that the standard enthalpy of fusion can be positive or negative. But you know that when we are converting solid into liquid, the ice will absorb some energy. It will absorb some energy. And it will change into what? Come on. Product. What is the product here? Water, liquid. So this is an endothermic reaction, my dear friends. So value is positive here. So I will call it as endothermic process, not a reaction. Because here substance is same, H2O, H2O. Only state is changing from solid to liquid. So it's not a chemical reaction, it's a physical process. So I can name it as it's a physical process. So standard enthalpy of fusion is positive, so it's an endothermic process, my dear friends. So here I will remove this negative sign now, and I will write down that this standard enthalpy of fusion is positive. So how much of energy is required to convert 1 mole of solid in its standard state into the liquid? We require 6 kilojoules of energy per mole. That means with respect to 1 mole of water to convert it from solid state to liquid state. When we convert water from solid to liquid state, this process is known as fusion. And it's nothing but it's a physical process. Because only the state of a substance is changing, substance is remaining the same, my dear friends. And what are the standard conditions for this particular substance? The standard state of water is taken at 1 bar pressure and at the temperature of interest. The temperature of interest is 0 degrees Celsius here. And that 0 degrees Celsius is a constant temperature, my dear friends, which I mentioned here. Constant temperature is your temperature of interest. And here it is 0 degrees Celsius. And 1 bar pressure, that's a specified pressure for this particular process. I hope you have understood, my dear friends. Please make note of this. My dear friends, let's talk about now standard enthalpy of vaporization, my dear friends. The amount of heat required. The term here which I mentioned here, amount of heat required. That means we are supplying the heat. When we supply the heat, obviously the delta H vaporization will be positive. This amount of heat required is nothing but it will give you the enthalpy change, the standard enthalpy change of vaporization is positive because this physical process requires heat. So amount of heat required to vaporize 1 mole of liquid. That means you have to take 1 mole of liquid and you have to do its vaporization. And once you do its vaporization, it will convert into gas. So you are converting liquid into gas by supplying the heat. So it's an endothermic process. At constant temperature, my dear friends, this is your temperature of interest. Remember, this constant temperature is your temperature of interest for this process. Why I call as temperature of interest? Because for this physical process, temperature requirement is different. And that is the boiling point of water. When you boil the water liquid, it will change into gas. So obviously I will take the boiling point of water, that is 373.15 Kelvin. Or you can take it as 100 degrees Celsius. Because at 100 degrees Celsius you can boil the water and it will change into the gaseous state or vapor state. You can also call it as vapor state. Gas is here vapor state. So you are converting liquid. How many moles of liquid you have here? You have a 1 mole of liquid, man. And you are vaporizing the 1 mole of liquid and obviously it will change into the vapor state, that is gaseous state. Temperature required here is 100 degree because water will boil at 100 degrees Celsius. So it will change, liquid will change into gaseous state. So now this is our temperature of interest. You can also call it as 373.15. We have to fix this temperature. So I can also call it as, it's a constant temperature for the process. So for this particular process of vaporization, the temperature requirement is 100 degrees Celsius. So that is our constant temperature. It's also called as temperature of interest. And now this is a standard pressure here, that is 1 bar pressure. Okay, no need to change that. Now during this process, when you are converting 1 mole of water liquid, okay, into the 1 mole of water gas, okay, and through the process of vaporization. So my dear friends, you heat the water at 100 degrees Celsius and at 1 bar pressure, then what will happen? You will be able to convert 1 mole of water liquid. You will be able to vaporize 1 mole of water liquid, and obviously it will change into the vapor state. That's true. And now what is my point? During this process, heat energy is required. Yes. So how much of heat energy is required? Yes. That is represented here by delta H vaporization, the standard enthalpy of vaporization. So how much of energy is required, my dear friends? 40.79 kilojoules per mole. If I want to convert 1 mole of water liquid, yes, into the gaseous state, I have to supply 40.79 kilojoules of heat energy. So obviously this is a endothermic process, not a reaction, because the substance remains the same, H2O and H2O. Only the state is changing, liquid is changing into gas. So when only state will change, but substance will remain the same, it's a physical process, my dear friends. And this is all about the standard enthalpy of vaporization. Please make note of this. Now let's talk about enthalpy of sublimation, my dear friends. And you know what happens in sublimation process? You are converting a solid directly into the gaseous state, and this process is known as sublimation. So during this sublimation process, what will be the standard change in enthalpy of sublimation, or what will be the value of standard enthalpy of sublimation? So we have to check it out. My dear friends, the standard enthalpy of sublimation, okay, can be positive or negative, but usually if you look here, it is positive, that is endothermic. So that means during sublimation, when you are converting a solid directly into the gaseous state, yes, energy is required. You are supplying the energy. Okay, so obviously it's an endothermic process, my dear friends. So what is important here? Have a look. The amount of heat required to convert 1 mole of solid directly into gaseous state. So you are converting a solid directly into the gaseous state at constant temperature, my dear friends. And here this constant temperature taken for carbon dioxide is 195 Kelvin. This is your temperature of interest, my dear friends, and 1 bar pressure. So this is known as standard enthalpy of sublimation. Have a look here now. So my dear friends, I am taking 1 mole. I am taking 1 mole of dry ice. Now you will be thinking, what is this dry ice? Dry ice means basically solid carbon dioxide is known as dry ice. So this carbon dioxide is in solid state, so I call it as dry ice. How many moles I am taking? 1 mole. And I am converting this solid directly into the gaseous state. I am doing sublimation, so I am getting the gaseous carbon dioxide. So this process is taking place at which temperature? 195 Kelvin, that's a temperature of interest, and at 1 bar pressure this process takes place. And what we have observed, that the standard enthalpy of sublimation for carbon dioxide, okay, is 25.2 kilojoules. That means for this process we require this much of energy, so it's an endothermic process. Because here you can see that CO2 and CO2 substance is same, but only state is changing. You are changing from solid state to gaseous state. That means when state of a substance changes, we call it as a physical process. But substance is same, carbon dioxide and carbon dioxide. So if we want to convert 1 mole of carbon dioxide in solid state, okay, from solid state into the gaseous state, we require this much of energy. So 25.2 kilojoules of energy is required to convert 1 mole of dry ice, that is solid carbon dioxide, directly into the gaseous state. at 195 Kelvin temperature and 1 bar pressure. These are the conditions, my dear friends. Please make note of this. My dear friends, now let us talk about standard enthalpy of formation. You can also call it as standard molar enthalpy of formation. The standard enthalpy change, that is your delta HF naught, standard enthalpy change, whether it is positive or it is negative. Okay, we have to find it out, whether it's endothermic or exothermic. Which thing? Standard molar enthalpy of formation. Mostly the formation reactions are exothermic, means heat energy is released. So obviously you can mention here that the formation reactions are exothermic, that means energy is basically given out, it's released. So let's go further. For the formation of 1 mole of a compound, this is very much important, remember this. So for the formation of 1 mole of a compound means you are making 1 mole of a compound. Remember this point? Second thing, from its elements. So that means 1 mole of a compound is made from its elements. Have a look here. Let us suppose if I have H2O. How many moles are there? 1 mole. I want to make 1 mole of H2O. And I should make it from its elements. Who is the element here? I should make it from H2 and I should also make it from this O. O can be written as half of O2. So I made 1 mole of water, my dear friends. So 1 mole of a compound. So 1 mole of a compound I made from its constituent elements. You can also mention here from its elements I wrote. You can also write down from its constituent elements. So what are the constituent elements in H2O? Hydrogen and 1 oxygen is here, that can be written as half of O2. So this reaction will give me the standard enthalpy of formation. For how many moles of a compound? For 1 mole of a compound, my dear friends. Now let's go further. And these constituent elements have to be in their most stable states of aggregation. Means they should, aggregation means actually in combination. Like if we talk about their most stable states, and their most stable states are also called as reference states. And reference state, you should remember here, it is taken as at 298 Kelvin, or you can take it as 25 degrees Celsius and at 1 bar pressure. So what is the meaning? If I take these constituent elements from which 1 mole of a compound is formed, these constituent elements should be in their most stable states of aggregation. And what is the meaning of in their most stable states? Those most stable states are called as reference states. And that reference state is taken at 298 Kelvin and 1 bar pressure. That means this process should be carried at 298 Kelvin temperature and 1 bar pressure. Then the constituent elements will be in their stable states or reference states. And then these constituent elements will combine and they will give me the 1 mole of a compound. And then I can calculate the standard enthalpy of formation, my dear friends. So now, try to understand now here. I want to make 1 mole of water. Look here. Formation of 1 mole of a compound. So I am making 1 mole of water from its constituent elements. What are the constituent elements? O2 and H2. So I can call these two as, my dear friends, as constituent elements. And this one I can call it as 1 mole of a compound. And which compound is this? This is water. And now see in this process, during the formation of 1 mole of water, from its constituent elements, hydrogen and oxygen, how much of energy is released? The energy released is minus 285.8 kilojoules. And that is the standard molar enthalpy of formation. Why molar enthalpy of formation? Because 1 mole is formed here. That's why we call it as standard molar enthalpy of formation. So remember, molar enthalpy of formation or standard molar enthalpy of formation is taken for the formation of 1 mole of substance from its constituent elements. Now have a look. Now here we have methane. How many moles of methane? I need 1 mole of a compound. So 1 mole of methane is a compound basically here. Is formed from its constituent elements. So these are the constituent elements. Yes? And during this process, what happens? The standard enthalpy of formation is minus 74.81 kilojoules. That means when 1 mole of methane is formed from its constituent elements, carbon, graphite, means carbon in the form of graphite plus hydrogen. Okay? So this much of energy is released. And now my dear friends, if you look at this particular reaction, you will find out that here I am getting 1 mole of ethanol. So here 1 mole of ethanol is formed. 1 mole of ethanol, okay, is formed here from its constituent elements. Who are the constituent elements in the ethanol? If you look here, the constituent elements are carbon, hydrogen and oxygen. So I am taking here carbon, hydrogen and oxygen. So from them I am making 1 mole of ethanol. And during the formation of ethanol, some amount of energy is released. How much is that? Minus 277.7 kilojoules of energy is released during the formation of 1 mole of ethanol. And during the formation of 1 mole of methane from its constituent elements, minus 74.81 kilojoules of energy is released. And during the formation of 1 mole of water from its constituent elements, how much of energy is released? Minus 285.8 kilojoules of energy is released. Now what is my point is that this hydrogen in gaseous state and oxygen in gaseous state will be considered as the most stable states, remember. And here carbon as graphite and hydrogen as gas, they will be considered as most stable states of aggregation. And here carbon as graphite, hydrogen as gas and oxygen as gas, they are the constituent elements in their most stable states. And the temperature should be at 298 Kelvin and the pressure has to be 1 bar if I talk about the reference state, my dear friends. I hope you have understood all about the standard molar enthalpy of formation. In all these reactions you have seen that 1 mole of a substance is formed from its constituent elements. Yes? So this is all about the standard molar enthalpy of formation. Now we can do some comparisons after this. Please make note of this particular thing and remember these expressions as well. Friends, now you have understood the standard molar enthalpy of formation, correct? Now let us discuss about a key point here. What is that? I have given you this reaction where the H2 and Br2, okay, these are the constituent elements. These are the constituent elements. They are giving me actually here 2 moles, okay, of HBr. So I am getting here 2 moles of HBr, correct? Now look at this reaction. These are also the constituent elements. Why we call them as constituent elements? Because your HBr is made from H and Br. So these are the constituent elements which make HBr. Yes. Now here I have 1 mole of HBr, my dear friends. Now I have not mentioned anything here. I did not mention here standard enthalpy of formation, or here also I did not mention standard enthalpy of formation. I am not using any term here. Let's suppose if I use here F here, it becomes standard enthalpy of formation. So I am avoiding F. Now you have to tell me that out of these 2 reactions, the first one and the second one, out of these 2 reactions, which one gives me the standard enthalpy of formation? Is it the first one or the second one? Yes. In first one I am getting 2 moles of HBr. But in second one I am getting 1 mole of HBr. And I told you the definition of enthalpy of formation. That is basically the formation of 1 mole of a substance or 1 mole of a compound. In which reaction 1 mole of a compound is formed? So I will write down here, when we talked about delta H F naught, it was formation of 1 mole of compound from its constituent elements. So when this delta H naught F, it discusses about the formation of 1 mole of a compound. But how many moles of compound are formed here? 2. And how many are formed here? 1. So my dear friends, this is your standard enthalpy of formation. Or you can also call it as standard molar enthalpy of formation. So this is your standard molar enthalpy of formation. And this is only taken for, remember, for 1 mole of a compound. But in this reaction, how many moles of compound are formed? 2 moles of compound are formed from its constituent elements. Yes, pattern is same. But here 1 mole is formed and here 2 moles are formed. So for this thing, I cannot write down delta H naught F. This is not correct. So what I am going to write down here, my dear friends, I will write down delta H naught R. That will become the, come on, standard enthalpy of a reaction. So you can't write down it as standard enthalpy of formation because 2 moles are formed. Wherever there is a formation of 1 mole from its constituent elements, there you can use the standard enthalpy of formation. But here 2 moles are formed, so you can't write down standard enthalpy of formation. You have to write down standard enthalpy of reaction. Now let me see the relationship between this delta H R naught and delta H F naught. If you look yourself, how much is the value here? 72.8. And how much is the value here? 36.4. That means, my dear friends, okay, we will talk about like this. This is double. This is just 36.4 and the double of this is this because this is the formation of 2 moles. So relationship will be very simple here. Relation between delta H R naught and delta H F naught. Okay. So what will be the relationship, my dear friends? Do you think delta H R naught is equal to delta H F naught? No, because we know that this is 72.8 and this guy is 36.4. So this guy is double. So in order to make them equal, let us suppose I want to make these 2 terms equal, then I have to multiply this side by 2. So 2 into this particular thing will give me this particular thing. So relationship is like this. Delta H R naught will become equal to delta H F naught when we multiply here by 2. Because 2 into 36.4 will become 72.8 and these 2 terms will become equal. Now my dear friends, in place of this 2, yes, you can write it as n now. Because sometimes if you are making here, let us suppose, if you make here 3 moles for time being, then this guy will become 3. If you make here 4 moles, then this guy will become 4. So better we will write down now n. So I will write down delta H R naught is equal to n delta H F naught, and n stands for number of moles formed. During a reaction. So I hope, my dear friends, you have gotten this relationship. Delta H R naught, yes, is equal to n times delta H F naught. See here, if you make here 10 moles, then this will become 10. Yes, please remember that particular thing, and I will give you some little more information about this standard molar enthalpy of formation, my dear friends. Please make note. Dear friends, let's talk about one more concept. It may be a little confusing, but I will clarify this particular concept for you. Have a look here. Let's suppose I have taken one reaction. in this reaction what is happening? You are getting a 1 mole of calcium carbonate. Okay. So now this 1 mole of calcium carbonate which we have here is formed from constituent compounds, not from constituent elements. Sorry, it's made from constituent compounds. Correct? So when you are making 1 mole of a compound from constituent compounds, then it is not taken as a standard, molar enthalpy of formation. Standard molar enthalpy of formation is taken only, have a look. If you make 1 mole of calcium carbonate, let us suppose you have 1 mole of calcium carbonate. If you make it from its constituent elements, from calcium, from carbon and 1.5 times O2. So formation of 1 mole of, you are making 1 mole of calcium carbonate from its constituent elements. What are the constituent elements here? So from its constituent elements, this is calcium, carbon and oxygen, 1.5 times O2, that will become O3. Correct, my dear friends? So when you make 1 mole of calcium carbonate from its constituent elements, then only I can take delta HF naught. But when you are making 1 mole of calcium carbonate, look here, 1 mole of calcium carbonate, you are making it from constituent compounds. Who is the compound here? Calcium oxide and carbon dioxide. So here you cannot take this, because this is only used for what? When you make 1 mole of a compound from its constituent elements. What are the constituent elements of this? Calcium, carbon and oxygen. Yes? And these are not the constituent elements, they are the constituent compounds. So you are making 1 mole of a compound from constituent compounds. So delta HF cannot be taken here. But here you can take the value of delta HF naught, my dear friends. I hope you have gotten this little idea about this. So let me erase it. So now what I am going to write down here, I am not allowed to write down here delta HF. I can write down delta HR naught. Yes or no? Because it is the formation of 1 mole of a compound from constituent compounds, not from constituent elements. So remember that thing. So I can make even small note for you people. Delta HF naught is taken only when 1 mole of a compound is formed from its constituent elements. If it is formed from constituent compounds, 1 mole of compound is formed from its constituent compounds, then it's not taken as delta HF naught. I hope, my dear friends, you have gotten this idea. So now let us go further and understand this. And obviously it's an exothermic reaction. This much of heat is basically being liberated. So it's a standard enthalpy of reaction. This is the standard enthalpy of reaction. In previous concept I told you that delta HR naught is equal to N times delta HF naught. This thing we have written in the previous concept, correct? So let us relate this. Let us relate this delta HR naught with delta HF naught for this particular reaction. So let us see that. So I want this value, my dear friends. I want this particular value, minus 178.3 kilojoules per mole. So I will write down an enthalpy expression for this reaction. That is delta HR naught is equal to, my dear friends, summation of what? That is the stoichiometric coefficient right out here. Then I will take on the enthalpies of formation, my dear friends. I will take on the enthalpy of formation of products minus summation of, that is Bi, that is the stoichiometric coefficient. Then I will take on enthalpy of formation of reactants. So I will take the enthalpy of formation of product and enthalpy of formation of reactants. Then I can calculate delta H R naught for this particular reaction. And this delta H R naught should be equal to this much. So we have to prove it. So my dear friends, first of all we will see what are our products. Our product is here calcium carbonate. So I will write down delta H R naught is equal to. So the sum of the products, we have only 1 mole of a product here my dear friends. So AI will become 1. Okay. Then I will take delta H F naught value for my product. Who is my product my dear friends? Calcium carbonate. Yes, in solid state. Now you will think that where from I should take this value, because it's not given here. So have a look here. I have already written some values for you. Delta H F naught values at 298 Kelvin and 1 bar pressure. So for calcium carbonate, what is the delta H F naught value? Minus 1206.92 kilojoules per mole. Now you'll be thinking here the calcium carbonate will be made from calcium plus carbon plus 1.5 times O2. So when these things will react, they will give me calcium carbonate, and then at that time delta HF naught will be this much. So I know the standard enthalpy of formation of calcium carbonate now. That is minus 1206.92. These values will be given in the examination. You have to only put them here. Correct? Now, this is all about product. And how many moles of product we have? 1. Then minus we have to do the summation of the standard enthalpies of formation for the reactants. And here we have 2 reactants, calcium oxide and carbon dioxide. So I will write down here. Calcium oxide is basically also how many moles? Only 1 mole. So I will take here it as 1. So I will find out its standard enthalpy of formation, which is also given to me. So now standard enthalpy of calcium oxide is already calculated. Okay. So this value has been taken when calcium reacts with half of O2. So when calcium reacts with half of O2, that constituent elements, 1 mole of calcium oxide is formed from constituent elements. So this value has been taken. Okay. Now, my dear friends, we are knowing the value of the standard enthalpy of formation for calcium oxide. That is minus 635.09. Then finally we have 1 more reactant here, that is carbon dioxide. So plus 1 more reactant. And how many times it is? Only 1 mole is there. So 1 into delta HF naught. Then we have here carbon dioxide, which is in gaseous state. So my dear friends, now it has become quite easy. So now for carbon dioxide, if you look, we already have, it is given already in the question, what is the standard enthalpy of formation. And this carbon dioxide will be made from carbon plus oxygen, constituent elements. So first of all, you have to make calcium, carbon and oxygen to react to get 1 mole of calcium carbonate, and you have to calculate this value. Second thing, you have to make calcium and oxygen to react to get 1 mole of calcium oxide to calculate this value. And then you have to make 1 carbon to react with oxygen to make what? 1 mole of carbon dioxide to get the standard enthalpy of formation value. These values are already given to you. You have to only put them in this particular expression. But I am telling you that how they got these values. Yes, I know. When these values are given in the question, how they got the values, I am telling you that. If I write down directly for calcium carbonate, standard enthalpy of formation is this much, then you will be thinking, how come? Actually, you have to make calcium carbonate from constituent elements. Yes, I know. These are the constituent elements, constituent elements, constituent elements. Then you have to calculate the standard enthalpy of formation. So these values are given to me. I can put them here in this particular equation now. Have a look. So I'll get here delta H R naught. And here we have 1 mole delta H naught F. What is that for calcium carbonate? If you see, that is, my dear friends, how much? Minus 1206.92. Correct? Cool. After that we have minus. Then we have 1 mole here, and for calcium oxide, what is the value of delta HF naught? Minus 65.09. minus 635.09. Okay. Then we have plus of minus value carbon dioxide. What is the standard enthalpy of formation? It is minus 393.51 kilojoules per mole. So my dear friends, now this will remain minus only. This will become also, this will become plus, minus into minus plus, and this will become, this is minus here. Plus minus will be minus, but then multiplied with this minus, it will become what? Plus. So when you simplify this particular process, your value of delta H R naught should become equal to, the value should become equal to this expression now. That is minus 178.3 kilojoules per mole. So my dear friends, what we have done, let us understand this particular thing. We have taken a chemical reaction and 1 mole of calcium carbonate was formed here. And then you might have thought that I should take it as delta H F naught. Yes, I should have taken it as delta H F naught, but I did not take it. Why? Because here 1 mole of a compound is formed from constituent compounds. I need 1 mole of a compound from constituent elements. So it cannot be delta H F. It has to be delta H R naught. Correct? So enthalpy of reaction. And it is given to me. This value is given to me. That is minus 178.3 kilojoules per mole. And I want to prove it. So in order to prove it, what we are going to do is that we will take an expression for this particular reaction for delta H R naught. That is the sum of the standard enthalpies of what? Products minus sum of the standard enthalpies of reactants. I know this is my product and these are my reactants. And these values are given to us. Standard enthalpies of product calcium carbonate and standard enthalpies of reactants are given to me. And I told you how to calculate these things. I have told you already. Through these chemical reactions, you can calculate these standard enthalpy of formation. So I will put all these values here. This is our product, standard enthalpy of calcium carbonate, and these are the sum of the standard enthalpies of reactants, calcium oxide and carbon dioxide. After putting all these values right out here, now delta H R naught should be equal to this. If it is not coming equal to this, understand that our proof is wrong. So you can check it out and find out that it should be exactly minus 178.3 kilojoules per mole. I hope, my dear friends, you have understood this thing. Please take care of yourself. Have a great time. Yo-yo.